Hi, welcome to the Signal Path. In this episode, we're going to take a close look at this Tesla Model Y indoor cabin radar module. There's a lot going on in here, and I want to do a deep dive all the way down to the integrated circuit and analyze and exactly figure out how they've built something like this. And this has become a little bit of a tradition that every year before the IEEE Microwave Symposium Week, which includes the RFIC conference as well, that we do one of these off-the-shelf component analysis and really figure out how the die is even built, which is going to be super interesting. Now, this year at the RFIC conference is a special year for me because I'll be giving the technical lecture on Sunday, June 15. And it's going to be all about instrumentation and metrology. I believe this is one of those topics that isn't getting a lot of attention at universities. And it should, because instrumentation has come a long way. And people are kind of losing touch a little bit about what are the limitations and what are the strengths of some of the nicest and greatest instrumentation that are on the market today. So we'll talk about how do we make measurements, how do we get confidence in our measurements, and what are some of the limitations, really looking into some of the block diagrams. I think it's going to be a really fun technical lecture, and I'm looking forward to it. Now, one last thing I want to say is that every analysis that I do on these off-the-shelf components is done entirely based on my own knowledge. I have access to no confidential information and no proprietary material. I'm just looking at the data sheet and, of course, what I observe myself. So we're going to do X-ray, we're going to do X-ray fluorescence, Raman spectroscopy, microscopy of various techniques. There's a lot of cool things going on. Let's get started. And here is a radar module, and there's a lot we can learn by looking at how it is put together from the outside before we take it apart. It does have only one interface to the car, which makes sense, typically either an Ethernet or a CAN bus, as well as power, of course, which then reads the information from the radar, shares it with the rest of the peripherals on the car, and ultimately with the central computer. Now, keep in mind that this is an indoor cabin module, so therefore its environmental requirements are nowhere as stringent as what is required for an external 77 gigahertz radar, for example. It is attached to the cabin using this one screw and a clip. Hey, at least it's not glued on. And on the other side, on this side, we have the radome. That is where the radiation goes in and out of, so it will be interesting to examine what this material is made of. Now, on the other side, this metal body is going to be a heatsink because there's a lot of thermal mass and everything else that this can provide. It doesn't need fins really because the overall power consumption of something like this is not very high anyway. And there are two screws that probably hold the whole thing together. Now, given the thickness of this and the size of this is probably only a single PCB construction, which is unusual for radars because the material requirements, RF requirements, for the radar side of something like this is very different from the power supply and the processor side. But when things get really small, you can make a multi-material PCB and laminate them and kind of get away with it. Depends on the size, performance, cost, and everything else. But these things, I suspect, in volume are not very expensive. So yeah, there's no hermetic sealing again because it doesn't need to be. These things should not get wet, at least hopefully not. And then yeah, we should take it apart and see what else is inside of it. Now, one thing to consider, given the size of this and its functions not being critical for the operation of the car, just passenger monitoring, indoor cabin monitoring, and so on, it doesn't really need a lot of customization. So I suspect that it is almost made entirely of just cuts as some components off the shelf that you can just put together. So even though it's labeled Tesla, I suspect that it's really just a packaging that is made by them, maybe the antenna design, but the rest of it is just going to be something that they have probably bought. We're going to find out exactly who makes all the devices. And let me also finish this equation. It's been kind of driving me crazy. There we go. And with removing two screws, we can remove the back over here. And there it is. Yeah, we see a lot of thermal pads. As it is common in automotive applications, they use very thick pads here because it reduces the tolerance requirements between the heatsink and everything else, and it's fairly good for vibration at the cost of some thermal conductivity. We'll have to clean that up so we can see what kind of devices are underneath it. And it looks like that the interface to the outside is actually just press fitted. Is it? Yeah, I think so. I don't see any solder on those interfaces. We should be able to pop this guy out. This is also not that uncommon. Yeah, there it is. Makes the assembly easy. Yeah, this is just press fitted into here. So we'll take a look at the radome later. You can see those pins are embedded into the plastic molding. And here's the main board. It's going to require a lot of analysis. And on this side, yeah, here's our antennas. We do have another shield here where the IC is underneath. Nice attention to protecting that device from various internal reflections and other types of picking up other EM waves you don't want to pick up. It's very important for radar. Yeah, we're going to have to clean this up and take a really close look at it. So let's take a look at the back of the PCB here. This is where we have all of our DC-DC converters, passives, and all the thermal management. If you look closely, you can see a flooded via area, which are all thermal vias, allowing you to bring the heat from the radar SoC, which is on the other side, through the PCB and dissipate it on this side. This is very common. These thermal flood vias are going to help with multiple things, aside from the grounding, of course. And here where they put all the putty and all the thermal interfaces and take the heat out as much as possible. And that makes sense because on the other side is where the radome is. And there's really not not an opportunity to take heat away from that side. So all the management has to be done on this part of the board. We also have several very sophisticated buck converters here, and they also have thermal putty all around them. For example, this chip over here is a quad buck converter with multi-phase outputs, and you can see there's 1, 2, 3, 4 inductors here. So this can have 4 independent outputs. Pretty sophisticated. It has internal memories. It can monitor the amount of current and the voltage, and it has SPI interfaces and digital control. It's pretty amazing what they can do. This is actually automotive grade. There's another one over here which has a spread spectrum, another buck converter here, and that is also made by TI. A lot of TI components. There's also some memory here, probably for calibration, some kind of a firmware revision, whatever it may be, that this can be interfaced through a serial interface as well. A chip missing in here, probably not needed for this revision of the board. But yeah, a lot of passives over here, a lot of interesting power management. So these VIAs go all the way through. Now on the other side is where we're going to find the really interesting RF components. Now at the heart of this, there is a TI 60 GHz SoC radar chipset. I'm going to go into the detail of the design of this chip. We're going to even look at the die itself. But for now, let's take it as a black box, a radar with 3 transmitters and 4 receivers. And you can see that the feed lines of the receivers and the transmitters are orthogonal to each other, but the feed lines to the antennas are in the same polarization. So the antennas are operating in the same polarization in both cases of the transmitter and receiver. You can see that the feed lines start with coplanar waveguides converting into strip lines and then going into a patch antenna. This patch antenna being fed from a strip line has multiple parameters that can be used to tune it. This little inlet that you can see, this little gap over here, brings the phase center deeper into the center of the antenna, allowing you to further tune the antenna to the impedance and performance you're looking for. And of course, the dimensions of the antenna and everything else are going to determine its center frequency. Now they have a nice opening over here, allowing to get nice directivity from the antenna, and the ground plane on the other side, tuning it so that it has a nice environment around it. And these antennas facing each other by definition means that they're not perfect because the outer ones are not the same as the one in the middle, but for the purposes of something like this, it really doesn't matter. This is inside cabin. You want these antennas to have a really broad range of coverage, just covering the entire area inside. That's why they have chosen only a single patch as opposed to an array of patches. They don't really need to squint the beam and squeeze the beam down in any orientation. Very, very straightforward design. Now in between the antennas, you see all these squares with the little dimples in the middle. These are EBG structures, electromagnetic band gap structures, or sometimes people call them high resistivity surfaces. This allows you to isolate these antennas from each other significantly, essentially kind of creating almost like a band stop filter between them, not allowing any surface propagation of the waves between the transmitter and the receiver to happen on the PCB. And every one of these little squares is blind via connected through the substrate material, so the substrate itself is also flooded with vias, not allowing any substrate modes to be picked up. A lot of attention is needed here because in a radar, when you have a transmitter, you don't want the transmitter to talk to the receiver through the PCB. That's pointless. You want the signal to leave the PCB completely, bounce against the target, and come back. At the same time, that's why they have this cover. This cover completely isolates the SoC from everything else and doesn't allow this part of the circuit to pick up any signals from the radar signature itself. So completely blocking everything, and not to mention all the digital noise and other things, completely confined within that area. Although these lines can pick up some signal, in a well-tuned environment like this, the antenna is going to be the highest gain by a wide margin, and that's going to really determine the signal coming back. Everything is fairly close together in this case, but it's okay. Again, for this purpose, this is really simple. They're basically doing the bare minimum they can. But the EBG certainly helps isolation. You can see via stitching here on the surrounding areas as well, and that means that there's no signal leaving from the edges of the PCB. Nice confined design, low gain antennas, broad beam, allowing you to very easily detect things inside of the cabin. Now this material over here is very different from a material on the other side, because on this side, we don't need to have RF performance. So they have, of course, a different high performance PCB material, whatever it might be. It doesn't really matter, but as long as it can provide good signal performance at 60 gigahertz. Yeah, very nice and compact. There's a crystal over here that's to feed some of the SoC functionality. There are some other lines over here, probably SPI and digital and everything else. You can see the EBG extending all the way out here, flooding this entire area. These vias, of course, don't go all the way to the other side. They're only for this top layer, which is the high performance RF layer. But yeah, looks pretty good. So I am going to remove this from the board so we can take a look at the die and get rid of the packaging. But I was going to x-ray this, but really is not much to look at because the feed line of the patch antennas are all on the same layer. So everything you see RF is confined to this layer alone, as well as the ground, of course, with the vias. But really there's not much to look at. This is as compact as I think you can make it because it's not super high performance. This design is not meant to be. It's going to be good enough for what they're looking for. Now, if we go ahead and remove the package from the PCB landing zone itself, from the footprint, we get further insight on how everything is put together. I've also removed the shield from around it, so you can see the landing zone, the footprints of the shield. We'll come back to that in a second. So if you look at the back of the package, there's a lot going on there. This is a fairly complex package, transitioning from the die with its own distribution layer, then ultimately creating the BGA grid that lands on the PCB. The RF ports are very clearly visible, so there's a lot of transitions going on inside the package too. We have vertical coaxial transitions ending into coplanar waveguide. So this is an RF port right down the middle. You can see surrounded by grounds, and these grounds land very nicely over here, creating a beautiful transition into this coplanar. And of course, the coplanar continues turning into microstrip and then going into the inlet of the patch antenna. Now, the rest of it are going to be power and other kind of signals to control this, but these transitions and isolations from each other on this board are pretty critical. And so, you have two ports of the radar here, so they really, really need to be well isolated, and I think these grounding structures achieve that fairly well. And the landing zones of the actual shield are visible with some solder mask around them just to control how the solder reflows over there. And then there's a little tiny windows where these things have to go under the shield, so that has to be sufficient opening so that there's no some impedance discontinuity over that transition. But given the size and the distances here, I think this coplanar waveguide is dominated by the ground on each side anyway. So it looks pretty nice. Now, having said that, there's two other things I want to look at. Of course, we want to get rid of this package so we can take a look at the die itself. In the meanwhile, we will destroy all the transitions and everything, but it doesn't matter. I think we have a fairly good idea of how this is put together. The other thing I want to investigate is the surface finish of these antennas and the traces, because I think this must be a silver immersion finish, but we can find out exactly by doing an X-ray fluorescence on this board and finding out the material composition of the PCB. You can even find the thickness, but that requires a little bit further calibration to get that information exactly. So there's a lot to do, one thing at a time. X-ray fluorescence first. I also took an X-ray of the package once I removed it from the board, and it is a really complex package. In fact, this is far more complicated than that entire PCB of the radar module itself, and the chip is pretty large. I mean, it occupies essentially all of this area. Some really beautiful transitions to vertical coax to coplanar waveguide. We can see the transition here, tons and tons of bumps from the die onto the package interposer over the digital section. A lot of attention to detail, very high resolution on the package itself. But yeah, this is pretty complicated. I'm actually surprised the amount of stuff that they've done on this package and transitioning in and out of it. Part of it is because the DSP is so big, and of course we have multiple RF channels. But yeah, it's really beautiful work there. And I have placed the PCB inside the X-ray fluorescence machine. I did a repair video on this, but I haven't done a follow-up video where we talk about the fundamental principle operation of fluorescence. We'll do that later. But for the time being, the PCB is right there. Let's take a look and see what the instrument says. So here's the view from the live camera inside of the fluorescence machine, and you can see I'm looking at one of the antennas. I can turn the laser on. We're right in the middle of the antenna, and that's where the X-ray is going to hit. Now, depending on how much silver there is, we will detect some counts coming back indicating that. But the majority of this is going to be, of course, copper, because that's where the traces are made of. Let's do a 30-second exposure on this and see what it returns. Okay, it's generating the spectrum. So this tone here is primary copper, which is not surprising. Oh man, there's very little silver in here. You can see this tiny little blip over here is an indication of silver. So it's almost nothing. Let's it's around this area right here. Yeah, it's almost nothing. So I'm probably not going to tell us much, but let's see what happens when this 30 seconds is over, if it tells us there's any silver at all. If not, we'll have to look at the counts individually to convince ourselves. Yeah, no, it tells you there's no silver, but I'm pretty sure there is, and it does tell you that most of it is, of course, copper. There's some calibration shift, so there's some lead in here, tin in here, and that's because it's nearby. On the other side, there is solder, and so it's detecting some of that. But let's go ahead and look at the counts themselves, because the counts are going to be more meaningful even if the amount is really small. So here, this first count, if you look at this first count, this is a count of silver here. So we should be able to measure it based on that. Let's do exactly the same measurement. This time just purely focusing on the counts. And there it is. So there's our spectrum again. So silver is right around here, and we'll see how many count. There you go. You can already see there's 234 counts per second, and that is indication of silver. The majority of it is green, 8100. That's all copper. So there is definitely some silver in this. It's just that it is extremely thin, which is a little surprising. They probably didn't want to do a lot of silver immersion. Again, the performance is most likely not critical here, but there is definitely some silver. Once this is over, we'll see the average count, and we can identify that from there. Let's see, there it is. Yeah, 226, that's indication of silver. 8100, that's copper, and the rest of them are some of the other elements. But I want to convince myself that there are boards with silver immersion that are actually detectable immediately. Let me show you a different radar board. So this is another 77 gigahertz radar board that I looked at. This one used Infineon chipsets. So we can do X-ray fluorescence on this one. You can see the similarity in the color, and this has been sitting outside for a while, so the very classic silver tarnish is beginning to form on it. This will eventually develop the same thing. But if we measure this, we should see hopefully more silver on this and convince us that the X-ray fluorescence is doing the right thing. And here is our other radar board, again looking at one of the linearly fed antenna arrays here right on the surface. We're looking right down the middle as well, doing the same thing. 15 seconds is more than enough. Here we go, and let's look at the spectrum again. So here it is, mostly copper again, not surprising. And here again we see some silver, but a very, very small amount. So let's see if this detects that. This one should have more silver finish on it. And let's see if it actually detects it as part of the percentage of the composition this time. Yeah, there it is. Look at that. There it is, silver right there. So yeah, the other board does have silver, just not a lot. In fact, if we do a count on it in exactly the same test as before, we run that, we should see a lot more CPS in here on this board. There it is. Look at that, 400. Yeah, over 400. So of course, it's going to be easier to detect that if there is more silver. It must have been below a threshold where it just says, yeah, there is nothing. But there is indeed silver on both of these boards. Well, while we're here, we may as well use a Raman spectroscopy to see what the radome material is made of and see if there's anything special there. So just put this in the front. Let's do a quick scan, and let's see what it tells us. Seems like it's just plastic polycarbonate, so nothing special at all. There it is, yeah, plastic polycarbonate with resin in it. And that's a little surprising because polycarbonate is not a very good RF radome, but it is really cheap. And the fact that it's black means it's probably not carbon powder based, must be some other black pigment that they put in there. But yeah, okay, now we know, just basic polycarbonate. Now, before we start looking at the IC itself, we should examine the block diagram of this SoC because it's a very large radar chipset with digital processing all built into it, and we should be able to use this block diagram to find our way around the chip itself. So this is broken into multiple subsections. We have a huge digital section, we'll get to that, and some internal calibration as well as digital front end for the radar part, and of course all the RF goodness in the front end. Now, we did say that this particular unit has 3 transmit sections, and it does, and it has 4 receive sections, and it does as well. Now, this supports both MIMO operation and beamforming operation. If you look at the transmit channels, the 3 PAs, each of them are equipped with a phase shifter. These phase shifters can flip the phase as well as have a 6-bit phase shifter built into them. So indeed, they support both beamforming as well as MIMO. Now, interestingly enough, you can't actually run all these PAs at the same time unless you bypass some LDO, probably for either some power management or just in general how they've designed their LDOs. Now, this is a 60 gigahertz system, of course, which means it's going to require 60 gigahertz RF, but it does have a 20 gigahertz synthesizer multiplied here by 3. This has a few advantages and disadvantages. Building a 20 gigahertz synthesizer is easier than a 60 gigahertz synthesizer. At the same time, if you, let's say, do a ramp at 1 gigahertz around 20, you get 3 gigahertz of RF bandwidth coming out. So there are advantages. The disadvantage is that you get phase noise multiplication and harmonic generations and everything else. Very classic trade-offs here. Now, on the receiver, we do have individual mixers after each LNA and an IF section and a digitizer. So this is a complete digital beamforming and digital MIMO processing that can follow this. So we don't have any beamforming that is happening in the RF domain on the receive side, but we do have it on the transmitter. And the data coming from the ADCs, lots of data coming in, it has some digital front end and decimation filter to reduce the amount of that, buffering it and everything else in order to do processing on it. There is a ramp generator built in, which works in conjunction with the synthesizer to generate the ramp you're looking for the FMCW radar operation. Temperature sensors, built-in oscillator circuitry, which is nice. This is most likely driving the synthesizer as well as everything else and providing clocks for the ADCs and a whole bunch of stuff most likely on the DSP side. A huge amount of BIST, built-in self-test section, which is also very interesting, as well as calibration. which means that on the die we should be able to see some designated paths that go from the PA into the LNA, and that allows you to do a complete internal loopback. Even though it's not shown on this diagram, there must be multiple sections in there allowing you to do this. Even sections to inject signals directly into the IF section as well as the ADC section to calibrate this as well. Given that they have put this in here, there must be a lot of internal self-test and calibration that this thing can do on its own. And this is not something that is programmed by the user. You can see it says TI programmed. So they must be running this at factory or even during power on initially. So very cool. Again, super complicated. On this side, we have a Cortex processor in here. We have a DSP processor in here. We have radar memory and a whole bunch of interfaces to the outside. Particularly, we have CAN interface for the communication for automotive application, which is what this is going to be using. And it does have high-speed ADC outputs for essentially extending this and just getting the raw data out so you can do your own processing if you need a deeper memory and so on. But given the fact that it does have the DSP and the digital front-end decimation filter built in here, all the Fourier transform and binning and all the radar stuff can happen inside of this chip, really simplifying a system that can use this. This is really good if you only want a single radar chipset, because you drop this in and you have everything covered. For larger systems where you have to have a very large aperture, they're not typically done this way, because then you have a lot of data you have to cover between them. You're replicating a lot of digital systems you don't need to. But that's a different discussion there on overall radar architecture. A lot of SPI, all the other things, and there's I believe a whole bunch of LDOs in here, some processor protection in here, some encryption even included. Yeah, so there is a ton of interesting things in this. Now, we're not going to see much of this when you look at the die, because it's all going to be digital synthesis. And I don't know what process this is in. Maybe 22 nanometer FDX from Global Foundries. It could be some other node. Maybe it's just a bulk CMOS node. I'm not 100% sure. But having said that, this is all going to be covered by metal. So you're going to see that there is a lot of digital section, but you won't see much. But this over here, we should absolutely be able to follow some of the signals on the die itself. So let's go take a look. And here goes the package. I feel bad destroying such a beautiful work of RF engineering inside the package itself, but that's the only way to get the die out. Well, here's the die, and in fact it is so large that I cannot look at it all at once under my high magnification microscope, but I did want to give you a bird's eye view on it before we zoom into various sections. So you can see very clearly that this entire section of it is covered with metal. And look at how many bumps it has, providing a really nice ground and VDD connection to all the DSP and the Cortex processors and everything, memory, all buried here under the metal. In the meanwhile, I found out this is actually TI's own 45 nanometer RF CMOS process, which makes sense. Manufacturing it in your own fab and designing for it certainly has massive cost advantages, and you can customize the process if you ever need to. Over here, we do see the PLL section, very obvious by the size of these inductors in the VCO cores, for example. And then we do have a section over here, which is 1 PA, 2 PA, 3 PA, and the 4 receivers here with the LNAs in the front end. So we should be able to look closely and then examine each of these sections individually. And you can even see right at the edge of the board, it's tough to see from this view, but there are lines that are running between the PAs and the LNA inputs. Those will be the calibration and the self-test lines. So they're indeed there. And we see the RF distribution starting from the synthesizer going into both of these sections. So lots of really cool IC design that we're going to be able to examine on this. And here's the microscope view of the chip. And look at the amount of work that's gone into creating something like this. I would say probably tens of millions of dollars of development has gone into making these chipsets. They're of course reusing blocks and things, especially on the DSP side from many products, but wow, the PAs look very interesting and complex. Here's a synthesizer core. So I think we should zoom in one section at a time and go from there. Probably the synthesizer is a logical place to start because it is required to drive the PAs as well as the LO of all the receiver sections. So let's zoom in here. Now this chip has a cleanup PLL and a synthesizer. The synthesizer will have the ramp generator and everything built in, and the cleanup PLL probably provides additional references and some of the other clocking required, but they seem to be working in conjunction. Now we do see a very large core of a VCO in here, perhaps part of the cleanup PLL, ultimately synced to the external crystal that is used. But really the interesting part is the actual synthesizer at 20 gigahertz, which is also the ramp generator. Now there's a lot going on here that's worth talking about. So let's go down a little bit and we can discuss it. So it looks like we have two different VCOs. If you look carefully, the passives of these are slightly different sizes. Most likely this is two VCOs to cover the entire frequency range with the desired phase noise at 20 gigahertz. The two outputs seem to be combined. Now there are a lot of tricks you can play here. where you can overlap the range of the VCOs and you can turn one on as you turn the other one off and do phase alignment and actually maintain the chirp across it. It's not so easy, but people have demonstrated that in the past, where you can get a really nice phase stable across the chirp duration. Perhaps that is one of the things they're doing here. You can see very high quality factor from the core of these VCOs, again to be expected because you do want to have as low phase noise as possible. Now we do have the combiner here, there's some buffer appears over here, and then the signal ends up here. So we have a differential signal now coming out of the synthesizer. Now there's this entire section over here with some ground signal, ground pads. You can see there's actually multiple of them. There's one over here, and there is two more over here. Now interestingly enough, in this chip, there is no mention of this, but there are some other versions of this IC with very similar architecture where you can do multiple chip synchronization, what's called a cascaded radar. It allows you to use the synthesizer of one chip as master and then pass it to the other chip as the slave. This way, one master synthesizer runs the ramp and passes that 20 gigahertz signal, or whatever the LO may be, to the next chip, and it can follow along, and then you can have a much larger aperture. Cascaded radars are also not new, but of course this is a pretty complicated thing to do. It looks like these pads are perhaps for that purpose, and they just have these circuits in there and they're not using it in this version of the chip for whatever reason, but they certainly have it in some of the other ones. But ultimately these pads are used to either give the LO or accept the LO from the outside and then do that master slave synthesizer that I was talking about. Now ultimately, if you follow this along, we can find out what happens after everything is done. We end up somewhere around here. Now I believe that this section might be the frequency tripler that multiplies the frequency by a factor of 3. If you look at the passives in this buffer, they're considerably smaller than the passives in the buffers earlier. So there is some frequency conversion happening here. So then multiplication by 3 makes sense. Everything's still differential, which means that if you go a little bit higher, these differential lines over here are the ultimate synthesizer output. Regardless of whether you're using this as a master or a slave, at the end of the day, you'll end up with a ramp at 20 gigahertz over here, which then gets multiplied by 3 earlier. So this is here is now a 60 gigahertz signal. Now this signal can go from 60 to 64, and that tells you a little bit about the range of those two other VCOs with some overlap and everything else taken into account in order to achieve the 60 to 64 differential signal. So now that's our LO. We can actually follow it and see where it goes. There we go. It goes over here, and look at that. We get a splitter, which is exactly what we expect to see, because the LO signal has to be split between the transmit chains and the receive chains. Both of them need it. The LO going to the transmitter just goes out of the PAs, but the LO going to the receiver is going to be driving, of course, the mixers. Now we can follow the transmitter path first because it is quite a bit more complex. There we go. So we split the signal here. This one goes to the receivers up north, and then over here we come, and now we have to split this again because we have 3 transmit PAs, so we have to split that signal again and again and amplify it each time. Now 3 is an odd number, which means that if they're going to split it every time by 2, they're going to have one path that is unused, because if you split by 2 each time, you're going to end up with 4. And check it out. That's exactly what's going on. Look at the signal coming over here. Again, split into 2, buffer. We have 1 used on this side, we have 1 used on this side. This is blind, which means it's terminated on chip, and then there is one on this side going to another PA. The reason they're doing this here is because they can just reuse this, and by doing that you get this really nice phase matching between all the paths, and you get a very predictable signal. So it's worthwhile doing this and just terminating it to nothing than to designing something else. It's just quite common in the situations like this. So let's follow one of these PAs and see what it looks like, because there is a lot going on in the PA section too. Let's see if we can follow this. So here's our 60 gigahertz signal coming here for one of the PAs. This entire section is one of the PAs. You can see that it repeats on this side. So it's just replicating it, which also makes sense because all the transmit chains are essentially identical. Here's a 60 gigahertz signal coming over here. Then it goes into this block. And if you look at this, we have 2 inputs over here, 2 termination in here, 2 over here, and 2 over here. This is, of course, a quadrature coupler, providing you with 0 and 90-degree signals. Now, it may be some other attenuation control or phase flipping or some adjustable delay and calibration might be built into this. There are many ways to generate quadrature signals. But at the end of the day, we're going to get our quadrature signal between these two. And then here we have our phase shifter cores, which are going to be various VGAs to do a vector modulation, and we combine everything. And then what we end up with over here is a signal, again at 60 gigahertz, whose phase and amplitude we can adjust very carefully. And that's, of course, a very classic RF phase shifter. And then we go over here, get some amplification, and look what happens here. It comes in this, and it splits into 2. So we have 1 amplifier on this side, and then we should have 1 more on this side. Look, it's perfectly symmetric, so we have a very symmetric structure. amplification, pass it over here, amplification, pass it over here, one more PA here, one here, one here, and one here. So we have 2 PAs driving 4 PAs, and then we have this really beautiful power combiner in here. I really like this structure because it's combining the output of 4 PAs and then a transformer coupling it into a single-ended output, because the chip has only single-ended outputs at the end. So this is a very, very nice PA structure. Now look how complex it is in terms of layout. Must have taken a long time to optimize. But the story doesn't end there. You can see that signal coming out of here, goes over here, and it's connected to our path. So that is ultimately our output. But there's an entire section over here with a line that's running in parallel to it. That's actually, I think, a directional coupler with 2 outputs, which means that you can do a detector on this side and a detector on this side, and you can detect the amount of power going forward and the amount of signal reflecting back. This is a very interesting and useful block, and is commonly used to detect both the output power as well as the reflected for antenna matching. So with this structure, you can pretty much determine what the impedance of the antenna is. And these on-chip structures for doing this and calibration, as well as fault detection and tuning and all, they're quite common at these high frequencies. There's a lot more going on still, because they are tapping off some of the signal from this side, and you can see they're bringing it out, and they're tapping one from the next one, and they're bringing that out, and those are our internal built-in self-test. If you follow this, you can see that they're tapping from multiple places of the PAs. Interestingly enough, in this PA, they tap a little bit on this side as well, but in this one they don't. So there's a slight difference between these 2 PAs, and that must be because the 2 PAs on the left are in MIMO configuration, but the third PA is only used as a phased array configuration. There is a ton of subtlety inside of these chips if you really wanted to dig deep. But if you look at all these signals, if you just not worry about all the details, you can see they're tapping them off, and if you follow it, they tap them, combine them. Remember, tapping and combining is really useful because you get a vector summation, so you can do even phase calibration. Pretty clever stuff. And then on this side, we can bring them in, and look what happens. They take all these signals, bring it all the way up here, and once you reach the LNAs, they feed them into the LNA from the other side. So they take the transmit signal, put it into the receive signal, and that's how you do a loop-back calibration. Each of these LNAs, this is the LNA section. There should be 4 of them, so here's 1. We go a little bit more north. Here's 2. We keep going. Here's 3. And then 1 more. Here's 4. You can see each of them gets a signal from the left side, and the actual output coming from the outside goes to the right. So that is exactly how the built-in self-test works. Now we can also examine this as well, because this is an interesting structure. Remember, we need a low noise amplifier front end, which I think this one does have. Let me adjust this focus a little bit better. There we go. So here's the input from the RF in. Here's the LNA front end, and look at this structure. Remember this? That's the quadrature hybrid that I was talking about that is used in the transmitter too. So they're using the same 90-degree generator as the phase shifter for the transmitter, but here they're using it on the LO to create I and Q quadrature down conversion. So they're basically generating 0 and 90-degree LO signals, and they come in together, and they go into section into the mixer. And once you mix it down, you get I and Q signals. So this is a radar that actually does quadrature down conversion, which has some benefits in radar. Of course, if you look at any of the radar theory, IQ conversion has a lot of advantages. The disadvantage is that you have twice as much data you need to process. And I think everything in here is the IF section. I'm not sure if the ADC is in here or not, but I do see some more analog RF things going on. The ADC in these chipsets is a delta sigma modulator. So here's the LO again coming in this way. So you can kind of see what's going on now. So the LO signal that I said was split on the other side. If I follow it all the way down here, there you go. This LO signal from here is going to all the receivers. You see it goes down the middle, up here, splits into 2, and then splits into 2 again, and drives all the LOs of all the down conversion mixers. So there's a lot of beautiful work going on here. And they're reusing a lot of the blocks, like these splitters are reused over and over again, and that's normal because you don't want to design everything from scratch. But it does look like that in between the LNA receivers, yeah, then maybe the delta sigma modulators are here. There's a lot of dense digital logic here. So it is certainly possible. But look at the amount of nice isolation they're getting there. They have these ground and VDD pads in the middle. All the pads are gone because the acid ate right through them. But these are just replicated stages. And then if you go all the way here, there is the massive digital section, so you just don't see it. It's all buried under the metal. But look at how nice it is. We can zoom in further and analyze every single one of these blocks if we really wanted to, but at some point it's just going to get too much. But it's definitely possible to see what's going on. The architecture is very clear, and if you put it side by side by the data sheet from the actual part, yeah, it becomes all clear. I like how they're using these blocks over and over again. And if you go down here, take a look at the PA again. Right, this one is a lot more damaged, but look at how nice these combiners are, the detectors. There's so much stuff on this chip. It's really quite beautiful. Yeah, it's interesting that these PAs are treated a little bit differently. It has to do with, most likely, with the MIMO. In the MIMO, when you do 0 and 180-degree flip, if you combine two PAs that are supposed to be 0 and 180, you can put a detector. When you add them, you should see nothing if the phase is exactly 180. So there's some tricks that I'm sure they're playing there as well. Let me focus on here. The chip is not completely flat. So maybe we can pick one of these things and look at a little bit closer at it. I don't know, maybe one of these power splitters would be interesting because it's quite simple. Yeah, let's zoom in the middle here so we can see it a little bit closer. So here's a closer look so you can see how one of these splitters actually looks like. So here's the 60 gigahertz signal coming over here. We do have a buffer driving this splitter section, then driving one buffer here on the left and one buffer on the right. The buffer on the right sends the signal out and goes into the final PA. And the one on the left is the quote-unquote blind one, just terminated and not used. And this structure is repeated over and over again, both in the transmit section and in the receive section. So there's a lot of interesting details. And if I focus a little bit through the layers, you look carefully, you can see all the underneath, how much more there is. This is we said it was a 45 nanometer RF CMOS process from TI, so you would be able to go and take a look at even individual devices. But yeah, very nice. Now this is exactly the same area of the chip, except now we're looking in DIC mode microscopy, and you can clearly see the surface roughness of these metals. Look how much detail there is, and if I focus just right, look at this pad. You can see that the surface of the pad is gone, the exposed metal, the aluminum top layer is gone, but underneath the pad there are all these other structures. It could be EST, could be some metal fill that they're using, but by looking at this we can actually look at how much surface roughness there is, and because there is not perfect planarization, you can see the structures under the metal layers. So some really cool imaging is actually possible here. And if I go a little bit, let's say this way, you can see some of the damage done by the acid, which is even more obvious, and you get some really beautiful colors as a result of that. Like for example here are these really interesting things that the acid does to the chip. Yeah, really cool. I mean, you can spend hours and hours just looking at all these structures. And with DIC, it is possible to adjust things in such a way where some of the angles of the metals will be essentially casting a shadow, so you can see what happens to these kind of inductors that have this hexagonal pattern and 45-degree angles on the chip. This is a pretty cool wallpaper. And there you have it. I hope you enjoyed this detailed analysis of this module. And we really should step back and appreciate the variety of analytical techniques that were used to look at this. I mean, we did X-ray of the package. We did X-ray fluorescence to understand the surface finish of the PCB. We did Raman spectroscopy to find the material of the radome, and a whole slew of just general microscopy techniques to look at the RFIC and even analyze how it is built and look at different layers and elements and components that are on the die itself. I mean, it's amazing that this is even possible. And this is thanks to the many Patreon supporters who support the channel and have been doing so for many years. You really make it possible. It's really easy to support the channel one time or through Patreon, and everything goes back into the lab so we can make more videos like this. And if you do attend the IMS RFIC conference, hopefully we'll run into each other and have a chat about all the cool things at the conference and the stuff that I plan to do here on the channel as well. I'll see you next time.